All right, so we're going to finish up chapter 17 with Le Chatelier's principle. And what Le Chatelier's principle looks at is once we reach equilibrium, if we put a stress on the reaction, on the system, how does the system react to get back to equilibrium? So basically what Le Chatelier's principle looks at is I have a system, it's reached equilibrium. The rate of the forward reaction is equal to the rate of the reverse reaction. We're getting no net change in our equilibrium concentrations. But let's say now we change a factor. So if you remember at the beginning of this lecture, I said, in theory, if I had a reaction in a container and I kept that container perfectly sealed where we didn't lose any moles of gas, we didn't gain any moles of gas, it was kept at constant pressure and temperature, that reaction should go on forever because it's just self-propagating in theory. What happens if we reach equilibrium, but now there's a leak in the container and we lose some of our product or we lose some of our reactant? How will the system compensate for that loss? Or we change the temperature, or we change the pressure. How will it compensate for that loss? Okay, to get back to equilibrium. So that's what Le Chatelier's principle looks at. Okay. So we're going to look at different stresses we can put on a system at equilibrium. So here's the example they give you. Okay. They tell you that 2NO2 gas is at equilibrium with N2O4 gas. And the way they have the reaction written is that it's an exothermic reaction. So now we got to go back to chapter 6. We have to go back to thermochemistry and talk about exothermic and endothermic and how do we tell in a reaction if it's exothermic or endothermic. So the reaction they're going to use throughout this explanation from the book is 2NO2 gas at equilibrium with N2O4 gas. And if you don't remember, our delta H at constant pressure tells us if we're exothermic or endothermic. Okay. So I'm exothermic, so this is a negative 58 kilojoules is how this would read. Remember, a positive delta H means I'm endothermic. A negative delta H means I'm exothermic. Now, in the slides, they basically take that information and rewrite this equation and say, well, if I'm an exothermic reaction, then heat is a product. And that's going to be important with Le Chatelier's principle. Heat is a product in this reaction, so that's why they write it as plus 58 kilojoules. If I was an endothermic reaction, that value would be over here. Okay? So on an exam, I don't know, in a week or so, okay, maybe 2 weeks today probably, or 2 weeks Thursday would be your next exam. If you're given a delta H, look at it. If it's negative, it gets added to the products. If it's positive, it gets added to the reactants. And that's going to help you out with Le Chatelier's principle. So if we go back to the PowerPoint, it says, given this information, as the pressure increases, the amount of N2O4 present at equilibrium increases. And as the temperature increases, the amount of N2O4 at equilibrium decreases. And the question is, how could we determine this by just looking at this equation? Well, there's certain rules and certain stresses that we can put on Le Chatelier's, or using Le Chatelier's principle, that we can put on equilibrium. The first is a change in concentration. Okay? And this one to me is the one that's the simplest to understand. If I take a product away, my reactant, or my reaction, I should say, is going to shift to replace that product. If I remove a reactant or take a reactant away, I'm going to shift towards the reactant side and replace what I took away. So it'd be like, okay, I have a refrigerator full of eggs. I use up all the eggs. So what do? I go and buy more eggs. Okay? My reaction loses product. In order to get back to equilibrium, I need to replace that. So I'm going to shift towards what I removed. Okay? Now, if I add a reactant or a product to a reaction at equilibrium, now I've got too much of what I've added. So I've got to shift away from what I've added. Now I have 18 dozen eggs in my refrigerator. I got to get rid of them. So I start giving them away and using them up and making omelets and cakes and muffins and whatever I could do to use up all the eggs. So if I add a reactant, I'm going to shift away. Add away, AA. If I add a product, I'm going to shift away, AA. If I remove a reactant or a product, I'm going to shift toward what I removed. So if we go back to our reaction here, if I were to add NO2, I would shift this way. If I were to add N2O4, just for completeness, let me put the G up there for my OCD. I would shift this way. If I were to remove NO2, I would shift that way. And if I were to remove N2O4, I would shift that way. So add a product or reactant, shift away. Remove a reactant or product, shift toward. Yes, my wife bought it for me for... my wife bought it for me for Christmas. I asked why she got me an AC/DC shirt. And then I realized what it was. All right, any questions on adding or removing a product and which way it'll cause a reaction at equilibrium to shift? The next PowerPoint slide basically shows this. Increasing the left-hand side or decreasing the right-hand side will cause a shift this way. Increasing the right-hand side, decreasing the left-hand side will cause a shift that way. So then let's move to the next stress. This is just showing the math behind it. And here is a sample problem you could try for homework. Okay. Sample problem 17.12. The effect of concentration on equilibrium and position. You could try that one for homework. Star that one. Like I said, the answer is there for you, so it works out. All right, what about, and I'll make it so you can see it here. What about changing the pressure? Okay. Now, we got to go back to our PV equals nRT fun. Okay. Because it deals with the volume and pressure meaning the same thing. All right. Or the same effect, essentially. So, if I increase the pressure of a system, okay, that's equivalent to decreasing the volume. If I decrease the pressure, it's equivalent to increasing the volume. So these stresses, either decreasing the volume or increasing the pressure, have the same effect on our reaction at equilibrium. Decreasing the pressure, increasing the volume, same effect on equilibrium. Now, what pressure and volume, okay, the effect that they have is based on the different moles of gas. Okay? Increasing the pressure and decreasing the volume will cause a shift to the side with less gas moles. Decreasing the pressure, increasing the volume would cause a shift to, if I could spell, more gas moles. Okay. So, in our reaction up here, if I were to increase the pressure or decrease the volume, I would shift to the side with less moles of gas. This has 2 moles of gas, this has 1 mole of gas, so I would shift this way towards N2O4. If I were to decrease the pressure or increase the volume, I would shift that way, back towards the more moles, NO2. I'm rocking my LCC sweatpants today. LCC Pride. Mark that off your Professor Bingo card. Did he show up in sweatpants today? I almost forget with 3 days off how to act like a human when I have to get back into the swing of things here. All right, questions on pressure and volume. Now, the question is, well, what if this was 2 moles or this was 2 moles, or what if it was all aqueous solutions? If there's no difference, okay, if there's no difference in gas molecules, or gas moles, I should say. P and V won't have any effect. A change in pressure and volume will have no effect on equilibrium. So if this was 2 and this was 2, there'd be no change. If this was all aqueous solutions and I changed the pressure or the volume, there would be no change. Okay? And the slides say that right there. Okay. So in this example here, they have a blue molecule, a yellow molecule to turn into a green one. If I increase the volume and lower the pressure, I should shift to the left. If I increase the pressure and decrease the volume, I'll shift to the right. Questions on that? You could try 17.13 for homework to start you off, because the answers are there. All right, another stress we could put on the system is, what do I mean by shift? Which side will the reaction favor, Tannen? Which side? I'm at equilibrium. What side, if I put these stresses onto the system, what side will I shift? Which side will I move to? Which direction will I go? Yep. I keep using the word shift because that's what's stuck in my head. So I'm at equilibrium, everything's cool. I remove a product. I shift towards the products. That means my reaction will move towards the products. Now, temperature is the same as concentration as long as you understand what the delta H values mean. Again, delta H, for if it's negative, okay, then I am exothermic. Heat is a product. If delta H is equal to a positive value, I'm endothermic, and heat is a reactant. Okay. If I understand that, rewrite the equation. So again, let's say I'm given this up here with a negative delta H. All right, negative delta H means I'm exothermic, heat's a product. Write heat as a product. Then you could treat it just like concentration. If I were, for this reaction, to add heat, I would shift this way. I'm adding heat. I'm adding a product. Therefore, I'll shift away from my products. The reaction will move away from my products to my reactants. That looks like feet, doesn't it? Add heat. If I were to minus heat from this reaction, take heat away, cool it, I would remove a product and cause the reaction to replace what I removed or shift to the right. So if I were to add heat to the reaction, this value should go down. This value will get used up. So I would go this way. This would get used up. If I were to remove heat, I would go this way, and this would get used up. The key is you can treat it like concentration if you understand what your delta H's mean. So first thing I would do on an exam, if I were given an equation like this, is to rewrite it like this, if I'm going to be asked Le Chatelier's principle kind of questions. Questions on concentration, questions on pressure and volume, questions on changing the temperature. This will be the reaction for Le Chatelier's principle that you do in lab, that you're given the data on. It's a pretty cool reaction. There's color changes. At equilibrium, it's purple. But the reactant side would be pink. The product side would be blue. Sample problem 17.14. So 17.12, 17.13, 17.14. Okay. For homework. What if I add a catalyst? What if I add something that speeds up the reaction? Well, first of all, catalyst's mode of action isn't to speed up the reaction. That's an end result. Again, a catalyst will lower the energy of activation, which does speed up a reaction. Catalysts don't have any effect on the equilibrium of a system. All a catalyst will do is get us to equilibrium a little bit faster. Adding a catalyst while I'm at equilibrium is not going to do anything. Okay. They don't participate in the composition of the Kc value or Qc value. All a catalyst will do is speed up a reaction. So catalysts have no effect on equilibrium. Here's a reaction, and we kind of drew this when we were doing the kinetics. By the way, speaking of which, your grades for the kinetics take home are up on Blackboard. Some of you sent me pictures, some of you sent me PDFs. So I graded them and I just put the grades up there. My scanner isn't working correctly, but your grades are up there on Blackboard for the take home if you handed a take home in to me. Okay. Here is a table that basically gives you the results of Le Chatelier's principle and the effects of a stress on a system. You could try sample problem 17.15 for homework. Okay. And that's the end of our chapter 17. So, homework that deals with this stuff here. From the PowerPoints. All right. 17.12 to 17.15 sample problems. And then page 780. Yep, 788. 788. $17.64 to $17.73. Okay. So that's Le Chatellier's principle. That ends chapter 17. Chapter 18 is up on Blackboard, and we'll start that on Tuesday. Or Thursday, I should say. Today's Tuesday. And whenever we finish that is when we'll have our exam. Now, messing around with Blackboard over the weekend, I can still, which I think will work out for us. It'll actually make it maybe a little bit even easier. I could still ask the questions like I would on a normal exam. I don't have to make them short, multiple choice. I could still ask the questions and give you multiple choice answers, which is what I think I'm going to do. So you'll have to do the math on a separate sheet of paper and then choose the right multiple choice, but at least the answer will be there for you. So that's what I'm thinking I'm going to do. So I'd still ask it in the same form as you've always taken an exam with me, except now you'll have to do the math, but the answer will be there as a multiple choice. I think it'll work out a little bit better than me coming up with like 50 multiple choice questions with math in there. I could ask it in the same format. No, I won't do 50 questions then, Brady. It'll still be like my exam where no partial credit then, because you have the right answer sitting in front of you, Kelly. That's the only difference. I won't make them worth like 20 points. Maybe I'll do like 4 of similar questions worth 5 each in multiple choice or something like that. But at least I can do it that way than 50 multiple choice. I have to decide. I'm still thinking how to make this as easy as possible for you guys. All right, let me stop the recording. I'll leave the stream going right there.